Understanding where our well is located within the subsurface is a key part of the geoscience interpretation process. It allows us to tie in information from multiple wells and also helps us ensure that the well that we have drilled is in the right place. Hey friends, I'm Andy, and if you already knew that, then welcome back to the channel. In today's video we're going to look at a library called Wellpathpy, where we can take raw survey measurements that have been taken from a wellbore and we can create continuous positional logs. When working with well log data, we often have multiple depth references. MD for measured depth, which is the depth along the actual wellbore, and we also have TVD, which is our true vertical depth, which is the vertical distance between the rig floor or rotary table and our position within the subsurface. Then we have TVDSS, which is our true vertical depth subsea, and this gives us our position of the wellbore relative to mean sea level. So the majority of the survey data that we obtain today is irregularly sampled, so it is only taken at specific points along the wellbore, and as a result we have to interpolate between these points. So we can't just do a simple linear interpolation, so we have to use mathematical functions in order to interpolate them properly. So in today's video we're going to see how we can use the Wellpathpy library to make these continuous logs. So let's hop over to our Jupyter notebook and see how we can do this. The first thing that we're going to do is install the Wellpathpy library. If you've not got it installed, you can do it in a number of different ways, through your command prompt or through the terminal window, but you can also do it within Jupyter notebooks by using the exclamation mark followed by pip install and then the library name. So I already have this library installed, but when I run this, it's just going to tell me that the requirement is already satisfied. But if you don't, then it will go through the process of gathering the Wellpathpy from pypy.org, and then it will install it onto your machine. Next, we're going to import some of the libraries that we're going to be working with. Now this is just a few of the libraries that we're going to use within this tutorial, and we will import a few later on. However, these will just get us started. So the first one that we're going to import is Wellpathpy, and we'll abbreviate that to WP. Then we're going to import matplotlib.pyplot as PLT, which is going to be used to create some plots. And finally, we're going to import numpy as NP, and then set the print options to have suppress is equal to true. And what this is going to do is it's going to suppress some of the scientific notation within the numpy arrays. And this just makes it easier to read, especially when we're dealing with values that are in the thousands, tens of thousands and the hundreds of thousands. So we will run that. So the next step is to load in our data, and we can do this simply by calling upon wp.readcsv. And within this function we pass in the location of our survey file. And the survey file must be in a particular format. So here I have one where I've got some of the survey data that we're going to be using. So we have 3 columns, one for measured depth, one for inclination, and then one for azimuth. And they're all abbreviated to these 3 abbreviations here, MD, Inc, and AZI. So when we call upon this function, we need to create 3 variables, MD, Inc, and AZI, which reflects that data within that CSV file. So we can run this, and the data is loaded in, and a Wellpathpy object is created. So if we want to check any of these variables, we can call upon MD, which gives us our measured depth, and this is the same data that was within that Excel spreadsheet, and the same with Inc, which gives us our inclination, or our deviation, and we can see that we've got values between 0 and 53.43 degrees. So now that we've got that data loaded into arrays, we next need to create a Wellpathpy deviation object. And we can do that by creating a new variable called dev and setting that equal to wp.deviation. And then we pass in our 3 arrays, MD, Inc, and AZI. So we've run that, and if we call upon dev, we will get back a collection of arrays. We see that we have MD, Inc, and AZI, and this is the same data that we have above, but now it is within a Wellpathpy deviation object. So usually what I like to do is visualize the raw data first to make sure that we've nothing erroneous and that everything seems to make sense in terms of the values. And we can do that visually using matplotlib. So here I'm using subplot to grid to create 2 subplots. And on the one I'm going to have inclination and measured depth, and on the second I'm going to have azimuth and measured depth as well. And I've just set the ranges of these so that they go between what we expect. So deviation should be between 0 and 90 typically, unless we're drilling horizontal or changing our inclination beyond 90 degrees. However, for the most part we're generally between 0 and 90. Then we've got our azimuth, which is set between 0 and 360 degrees, so imagine your compass points between 0 and 360. So if we run that, we get the following plot. we can see that we've got measure depth on the y-axis, and we can see the deviation and the azimuth. So the deviation, we can see that we're increasing our whole angle here, and then we're coming back to vertical, and then increasing it again, and then holding steady before coming back on the deviation, and then increasing it again, and then leveling it out at the end of the well. On the azimuth side, we can see that we're starting at 0, which is our north position, and we can see that we've gone towards the northeast, and then we take a swing around to the northwest and westerly direction, and then hold that, and eventually land the well in an easterly direction. So this just gives us a visualization of that well data, and we can make sure that we're reading values correctly. So with survey data, we've got sporadically sampled data with large gaps in between the measurements. So we need to resample our data so that we have a measurement, say every 1 meter or 2 meters or 5 meters, and that number will depend on the end use of that data. So for this one, we're going to be plotting our data every meter. And we're also going to be creating our positional logs, our northing and easting. That gives us our accurate position of where the wellbore is. So for this, we need to set the depth step to 1, and this is how regular we're going to sample the data. And then we're just going to create an array called depths, and it's going to range from 0 to the last value within the measured depth. So that will go to 3438 meters. And then we're adding on a value of 1, and then we're sampling it at every meter. So we can run that, and if I put in a new cell in here, and then we call upon depths, we can see that we've got a list which is going from 0 all the way down to our end value. So if I put in depths -1 to get our last value, we can see that we're going to 3438 meters. So next we need to create our continuous logs using the minimum curvature method. And this is a very common method to create continuous positional logs and survey data. You can find a link down in the description below if you want to find out the mathematics behind this methodology. To use this, we need to create a new variable called POS for position, and then call upon dev.min, and then we auto-complete that with minimum curvature, and then we need to call upon resample, and then we pass in depths is equal to depths. So we're passing in our array from up here into this function. So when we run that and then call upon the variable, we can see that we've now got our depth, which is continuously sampled between 0 and our last value 3073.816. And then we have our northing and easting positions, so this is where we are on an XY grid or a topographical view, and we'll see that in a second when we come to plot that data. So our original survey data is still sporadically sampled, and we can resample that data so that it is the same step as this one here, and we can do that simply by creating a new variable called resampled_dev, and we set that equal to pos.deviation, and then put our brackets in, and that will just run the calculation through that. So that will just resample our data, and when we call upon that variable, we can now see that we've got our measure depth going from 0 all the way down to 3438, and we can see that we've got some floating point precision issues here, which isn't really a big issue, but it's just something to be aware of. And then we have our inclination for each of those depth measurements, and the same with azimuth. So to be sure that we've actually calculated that data accurately, we can recreate our plot that we had above, but also add on these resampled curves. So we've got a resampled inclination here, and also a resampled azimuth. So we can run that, and what we should get back is two lines. One is denoted by the black circles, which is our original data, and then we've got the red line, which is our resampled data. And what we're looking for is agreement between them. And we can see that we've got them both overlaying each other, which indicates that our calculation has worked well. So now that we have resampled the data and created our positional logs, we can start to visualize our positional data, and we can do this through matplotlib. And what we're going to do here is create three plots or three subplots. One that gives us our topographical view, so our north-south versus east-west, and then we're going to see the variation in our east-west distance with depth, along with our north-south variation with depth. And when we run that, we get back our three subplots, and we can see we've got subplot 1, which is our topographical view, and we can see that we've started from 0 here, and then we're moving all the way down, and we can see that we've got this odd pattern with our well. We're swinging to the north and then back around, and then coming towards the southeast. And we'll see at the end of this tutorial how we can view this in 3D to get a better understanding of our well path. Then we've got our east-west variation with depth, and the same with our south-north variation with depth. So the purpose of doing some of these calculations is to get a TVD or TVDSS curve, and this gives us an indication of how deep the well is vertically with reference to the rotary table or Kelly bushing, and also with the mean sea level for TVDSS. And this is very useful, especially when we come to geological correlation and planning our next well, and also ensuring that we're currently in the right formations from our original well plan. So we can calculate this TVDSS data by creating a new variable called pos underscore TVDSS, so position TVDSS, and we will set that equal to pos dot to underscore TVDSS, and then we pass in our datum elevation. So this is the elevation of our rig floor or a rotary table or Kelly bushing, depending on what reference you want to use. And this is with reference to mean sea level, so we can say that we are 30 meters above mean sea level, and that is where our Kelly bushing or rig floor is. So we can run that, and then we can call upon pos underscore TVDSS, and we can see that we've got a similar array for our position data, and we've got our depth. And now it is slightly confusing that we're calling this depth when it is actually TVDSS, so that is just something to be aware of when you're calling upon these different variables. So it's always wise to name these variables what they actually are. So pos underscore TVDSS tells us that we've got our TVDSS data here. So looking at well positions on 2D plots can be very limiting, especially if you're trying to understand that wellbore's position and shape. So next we're going to see how we can create an interactive 3D plot in Python. But before we generate that plot, we need to position our wellbore in the right place. So we have northing and eastings associated with each well, and this indicates where that well is located. And what we're going to do is shift this position here, this 0, 0 position, and we're going to shift that to our reference data here, where we've got a reference northing and a reference easting. And then what we'd simply do is call upon pos dot to underscore wellhead, and that is going to set the surface northing to the wellhead northing that I've defined here, and then the same with the easting, and that will be set to this value here. So we can run that, and then we call upon pos underscore wellhead, and we can see now that we've got northing and eastings, and these are now starting at the datum points that we've specified here. So now that our wellbore has been referenced to the right location, we can move on to making our 3D plot. So for this, we're going to rely on Plotly rather than Matplotlib, and in my view this generates a much better and much more interactive experience compared to Matplotlib. However, the code is slightly more complex, as you'll see here. So we're importing Plotly and Plotly graph objects. Now I've done a few videos before in Plotly, and you can find them on my channel if you're interested in learning more about them. Next, we're going to configure the plot to render within our Jupyter Notebook. So if we're working within Jupyter Notebooks or Jupyter Lab, we need to set it up so that it is going to render properly. Next, we're going to configure our trace, and this is going to be our well path. So we're going to call upon graph objects, and then we're going to call upon the graph scatter 3D. And then we pass it in our variables, so our x, y, and z values. So our x is going to be our position wellhead, easting, and then northing, and then depth. Then we're going to set the markers, and we're also going to set them to a size 5 and opacity of 0.8. What we're going to have is individual markers that are all joined up together to form this 3D plot. We then create our data variable, and then bring that trace into a list, and then create our figure object, and we'll call upon graphObjects.figure and pass in our data. Next, we're going to update the layout, and we'll set the scene, and this is done with a dictionary. So we're going to set the z-axis, which is our TVD curve, and we're going to reverse that so that we're going from shallow to deep rather than the other way around, as you would expect with a standard scatter plot. Then we're going to pass in our x-axis, y-axis, and z-axis titles, so TVD, south, north, and west and east. And then we'll set the width and margin. So when we run this, it just takes a few seconds to generate, but when it runs, we can now see that we've got a 3D plot here. And the good thing about Plotly is it's interactive right away, and we can start moving around our plot, and we can start to see our well path, and we can start to understand how our well is being designed. We can see that we've got a vertical section here, and then we're coming round for a bit of a twist before coming round and deviating the well significantly to be able to land it within our target reservoir. Now we're on to our final section where we're trying to create a Pandas data frame of our resampled survey data and positional data. So when working with well log data in Python, it is common to work within Pandas data frames. So Wellpathpy does not provide a direct export to this format, so we can easily create a data frame, first by importing Pandas, and then we're going to create a dictionary object here called data. And we're going to set our column names, MD for measured depth, ASI, INC, TVD, TVDSS, etc. And then we're just going to set them to the various variables that we've declared above. So we've got a resampled deviation for .md, and then resampled deviation and calling upon the ASI and INC. And then we're also going to call upon our TVD, TVDSS, northing and easting positions, if we're going with the XY where we're starting from 0, but we can also equally change this to our variable that we created here, pos_wellhead. Next we've got our X and Y locations, so these are going to start from 0, and then we've got our northing and easting, which are going to start from our actual position of the wellhead. And then we're going to create the data frame simply by calling upon pd.dataframe and then passing in the data. And then we can call upon df, and we can see that we've got our data frame, and we're regularly sampled at 1 meter intervals. And we can see that we've got our azimuth, inclination, TVD, TVDSS, etc. all within this data frame. And then we can integrate that with our well log data so that we have a composite data frame if we want to work with that for machine learning or data visualization or other purposes. I hope you've enjoyed today's video and found it informative. If you have, give it a thumbs up down below, and if you want to see more content from this channel, click on that subscribe button and ding that notification bell. So thanks for watching, and until next time, bye for now.